We'll see, we get a few more people today. No, one person said, oh. So we're going to do our kind of main overview here, where we'll start with an example, and we'll look at it in a simplified manner. We won't kind of delve too deep into it, but we will come back later and look at all the intricacies. So here's our example. It's from the textbook. And the research question, a silly one, is do unattractive faces become more attractive with alcohol? So the classic beer goggle effect. And I tried to Google image this, and I managed to find an image that I don't think is offensive compared to most of the other ones. So in this study, this made-up study, they asked participants to rate either attractive or unattractive faces, and these were different groups. So these are between participant studies. We'll look at within participant later in a couple weeks, I guess. So you rated those faces on a scale from 0 to 10, and exactly is that interval or ratio? It's hard to say, but we'll just say it's it's continuous. And there were 6 groups, 8 participants per group. And so 3 of those groups just rated unattractive faces. And within that group, some people had a 0 blood alcohol concentration. Oh, these stand for that blood alcohol concentration. Some had 0.04 and some had 0.07. And then for other 3 groups, they kind of did the same thing, but in these groups, they just rated attractive faces. So of our 6 groups, everyone does a different condition, if you will. And then that depends on attractive faces, unattractive faces, and then what the blood alcohol concentration is. So here historical, some global context to this. Like this isn't a serious study, but 0.08 is, I believe, the legal limit in Texas. And most of the states, I did notice that in Utah, it's 0.05. And we switched to that a few years ago. And there's kind of a push to go to 0.05 as your driving is, significantly deteriorated at 0.05. I'm not sure if it's not at 0.04, but the higher the worse it is. So driving at 0.05 is better than driving at 0.08. Most of the world is already 0.05, so that may be where we're all headed. Interesting, I noticed some places are lower than 0.05. Serbia, Japan, and Uruguay are 0.03. And 0.02 in China, Estonia, Poland, and Sweden.
Is there anything higher than 0.08?
Oh, that's a good question. That I don't know.
That would be nuts. What if you have like a Tesla that can drive itself?
Yeah, if cars become fully autonomous, it wouldn't matter.
Yeah, but you can still override it, so I feel like 0.1.
I am not voting new government. Okay. So here are the data, and this is what we're going to analyze. So we have ratings, attractiveness of 0, no, not attractive. Assuming it went up to 10, but I think we didn't have to get higher than that. I think it was 0 to 10, right? Yeah, 0 to 10. Now we can see that rating attractive faces, it doesn't seem to matter if your blood alcohol is 0 or 0.7. Seem fairly comparable. We'll need to run the stats to check. I forget exactly which error bars these are. And then over here with unattractive faces, it does seem to depend on your blood alcohol, where the higher the blood alcohol, the higher you rate those unattractive faces. And eventually it seems to be unattractive faces are just as attractive as attractive faces. So that's our silly made-up data. Here's a bar graph is probably the best way to present that data, but SPSS, you often get line graphs, and line graphs, we often like to look at line graphs for interactions. So we will see the data like this a few times today too. So how could we analyze this? I guess, we could do a bunch of t-tests. We know that that's a little silly. So the Familywise error rate gets out of control. So we could do a one-way ANOVA with 6 levels, as shown. So if we do that, there would be 15 pairwise comparisons. So we use that formula there. And then we could use that 15 comparisons to calculate the Familywise error rate. And this is kind of a worst case, but it ends up being, sorry, there it is, 0.54. So that's, one method, but we're ignoring the organization and sharing of the data where, there's this split between attractive, unattractive, and then there's these, 0 blood alcohol, 0.4, 0.7. A one-way ANOVA, we're kind of ignoring that. And we can take advantage of that organization when it does exist with a factorial ANOVA, where we're going to kind of separate the influence of base type, blood alcohol, and then we'll also look at the interaction between those two things. Okay. And one issue with just a with a one-way ANOVA is that we're going to have a big hit to our Familywise error rate. So for this ANOVA, the way we want to structure it is it's going to be a 2-face type. So this is our first factor, face type. Are they unattractive or attractive faces? And 2 means that there's 2 levels, unattractive, attractive. And then our second factor is blood alcohol. That's 3 blood alcohol, meaning that there are 3 levels, 0.0, 0.04, and 0.07. We've got 2 factors. The first factor is 2 levels, and the second factor has 3 levels. So we call this a 2-way ANOVA because there are 2 factors. In the advanced class, we will look at 3-way ANOVAs, but you can mention a 4-way or a 5-way. I guess it's infinite, but I guess I wonder how many factors until SPSS won't run it for you. Any questions about our factorial ANOVA structure? Here's the data in SPSS, and this is on Blackboard if you want to pull it down for yourself. So it's a little hard to see. Well, let's switch to an SPSS. So we have the 2 columns that identify our conditions. So this column is the face type, and I put it 0 as unattractive, 1 as attractive. I use the label function under variable view to input those so that when you run the stats, it won't just say 0, it'll say attractive, unattractive, which is easier to interpret. And alcohol 0 is 0.01 was our 0.04, and 2 is our 0.07. And then these are each row is a participant. So this first participant was rating unattractive faces, and their blood alcohol is 0.0. And this is a mean, so I looked at a bunch of faces, and on average, they rated them as a 2. So that's our first group of participants. Those are our first 8 participants who are all in the same condition. And the next 8 are the next condition, and so on. So to run this in SPSS, I'll do that here, but the slides will show you if you need to go back and look at it later. So we're going to go to Analyze, and we're down in here in General Linear Models, Univariate. So new submenu for us. And we want to put in our dependent variable, which is the attractiveness of the face. Yep. And then we want to put in our 2 factors. We're going to put them as fixed factors, face type, alcohol. We're going to put that in here. Later on, we'll look at clicking some of these buttons, but we're just going to do very basic ANOVA to start. We'll say OK, and it's going to give us our output here. So just if you don't click any other options, you just get 2 boxes, which is kind of nice, but we will want some more details later. Let's go and look at these kind of zoomed in here. So with this factorial ANOVA, we actually have 3 tests, if you will. So with the t-test, there's 1 p-value. With the one-way ANOVA, there's 1 p-value until you get to post-hoc tests. Here we have 3 tests. We have a test For face type, is there a difference between attractive and unattractive faces? And this is essentially a t-test because there are two levels to face type. Kind of think of it that way. Alcohol, there's a test, doesn't make a difference if your blood is 0.0, 0.4, or 0.7. And that is basically a one-way ANOVA with 3 levels. It's almost. So we're testing that there and see, is it significant? Yes. What is there a significant effect of face type? Yes. But there's also the interaction between those two things. And that is shown here, the face type by alcohol interaction, a two-way interaction called the 2 factors. And it is significant as well. The way we report these is pretty similar to a one-way ANOVA. For face type, the degrees of freedom is 1, and then the second degree of freedom we use is the number in the air, so it's 1.42. We put in our F value, 15.58, and the P value is very small, so we can say it's less than 0.01. So we have a significant main effect of face type, a significant main effect of alcohol, and then we have a significant face type by alcohol interaction. So what do these mean? What do they tell us? So we're gonna kind of talk a bit about main effects and then interactions. Any questions so far? So main effects. What are main effects? And let's look at these visually. So I think that makes the most sense. So here's our data. This is the full complexity of the data. So if you think of a 2 by 3 ANOVA, 2 times 3 is 6. We've got 6 conditions. All 6 are shown here. But if we're thinking about the main effect of face type, all we're comparing are unattractive ratings or unattractive faces to attractive faces. So we don't care what blood alcohol is. We don't care what blood alcohol is here. We basically use the average across blood alcohol for unattractive faces and average across blood alcohol for attractive faces. So imagine, if you do this on a per participant level, but as long as you have equal number of participants, you can do that at the group level as well. So if we take these 3 values, we want to average them to just know what's happening with unattractive faces regardless of blood alcohol. So let's say this is about 4, this is about 5, this is about 6. The average of those would be 5. So unattractive faces, regardless of blood alcohol, the rating is about a 5 on average. When we've collapsed across or regardless of blood alcohol. Over here, we're going to average across these 3 because we don't care about blood alcohol here. We just want to know what is the average value for attractive faces. These seem to be 6.5, or maybe we'll just say 6. So 6, average those together is 6. So that's what we do when we talk about the main effect of face type. We don't care about blood alcohol, or we average across blood alcohol. And then here are those values. So I said about 5, about 6, that's approximately where we got. And the significant main effect of face type is essentially a t-test, because we just have 2 levels. And we saw that, yes, it was significant. We have the stats here. So we now know there's a significant difference between these 2. And visually, we can see that, well, unattractive faces are rated lower than attractive faces, regardless of what's happening with blood alcohol. And in this experiment, is that important? Well, there's an interaction. That's the most important thing. We'll get to talk more about that. But here, this is kind of showing us a manipulation check. That we've obviously picked images of attractive people and unattractive people, and we would hope participants rate them differently. And here is some evidence that they do. Yes, on average, you rate attractive faces higher than unattractive faces. Any question about our first kind of main effect, which kind of ends up just being a t-test? So let's look at our second main effect, and that one kind of ends up being a one-way ANOVA. Here, we go back to the full data, the 2 by 3, 6 condition data. Now we only care about blood alcohol concentration for the main effect of alcohol. So what we want to do is average across whether they're unattractive or attractive faces. So our first data point, we want to take these 2 data points and average them together. And that will tell us about one alcohol at 0.0, regardless of attractiveness. So we're going to take those two values. So if it's about 4 and 6, and we're going to get an average of 5. So we want to do the same thing for our orange values. Let's see, we've got about 5 and 6, so it's going to be about 5.5. So it's, yeah, the average is going up a bit. And then these two, if we say that 6 and 6, then the average is 6. So we're averaging across the factor that we don't care about in this case. And there are those data. Now, the test here, the main effect, and that's what we call it when we just look at a single factor, it's called a main effect of alcohol, so it's significant. And so you can think of this just like a one-way ANOVA. It's saying that yes, these three means are not equal. What is different about them, we don't know without doing some post hoc tests. So it could be that this group is significantly higher than that group, and this group is significantly higher than that group. So they could all be significantly different. Or it might just be the extremes. This one is significantly from that one. There could be different combinations here. We need to do some post hoc tests to fully examine this main effect. That's why it's sometimes nice when you have a factor with just 2 levels, because you don't need any post hoc tests. And we'll see how we can ask SPSS, just like a couple of weeks ago, to say, hey, do some post hoc tests on this main effect, the same way you would with a one-way ANOVA. Okay. Oh, we're going to do that now. So to do post hoc tests, let's go back to SPSS here. When, very similar to with the one-way ANOVA, when we input our ANOVA, we can say, hey, we want some post hoc tests. And we don't need one for phase type, so just at 2 levels. So we're just going to say, hey, give us some post hoc tests for alcohol. And just like before, we've got these 18 options. I'm not sure if it's going to let us pick these ones. Oh, let's see. What do I pick in my slides? I think I picked 2D, REG, WQ, because we saw those were a good balance between power, family-wise, air rate. And because there's actually only 3 levels, then Bonferroni is appropriate as well. Bonferroni is usually underpowered when there's 4 or more levels. So here we only have 3, so we can try. So if we do this below those 2 boxes we saw before, we now have some post hoc tests. And let's just look at those in PowerPoint. So if you decide to run multiple post hoc tests, the rule is that you have to go with whichever one is the most powerful, not which one you like the most. If there's a test that you really prefer and you only want to use it, then just run that. If you run multiple, you have to go with the most powerful. So we want to figure out which is the most powerful. So we can try to look at a comparison where we see a p-value comparing the same 2 conditions. Let's see, which one did I pick? So let's think about this comparison where here's 2P's results, here's Bonferroni, and REGWQ, remember, only shows up in this table. And 2P is also as a table like that. So here we're comparing 0.0 to 0.4 collapse across attractiveness, and 2P gives us a p-value of 0.178. And the smaller that p-value is, with other tests, the more powerful that test, because it's the same set of data. If we look at that same comparison with Bonferroni, the p-value is 0.231. So aside from saying these are both non-significant, what we know is that 2P's test for these data is a little more powerful than Bonferroni's. What about REGWQ? This is always a little trickier because you don't get a p-value for every comparison. You're only going to get non-significant p-values. But because this is non-significant, you should see this comparison down here. And let's see. So REGWQ, we've got 0.0, 0.4, and the p-value comparing those 2 groups is 0.077. That's our smallest p-value, so that must be the most powerful test for these data. So what that means is we should be reporting the REGWQ result because it's the most powerful. And we plot those results, we put our groups in ascending order, draw some lines over them. This is what we see. So the 0.04 group, oh, I think we have a chart here too, that'll help. Yeah. The 0.04 group is actually comparable to 0.0 and 0.7, which are a little smaller and a little bigger numerically. But there is a significant difference between the two biggest differences between 0.0 and 0.07. So it does seem that attractiveness does go up, at least between no alcohol and 0.07. So that's how we can fully analyze a significant main effect. When there's two levels, just like a t-test, you don't need to go any further. There could be 3 or more levels. Then you need post hoc tests, just like we saw in one-way ANOVA. And we haven't looked at the interaction yet. So any questions about our main effects? Right. So we have an interaction. Thankfully, there's just 2 factors involved. Things get more complicated the more factors there are, and that's why we're saving 3-way interactions for the advanced class. It's even hard to find textbook examples of 3-way interactions. I'm trying to remember if there's one in the textbook for the class. So I think in the advanced class, I actually don't use an example from the text. So I'm wondering if maybe they, does anyone know, are there 3-way interactions in the text? Okay, so here, remember we had a 2-way interaction. And with a 2-way ANOVA, if you have a significant interaction, that actually overrides significant main effects. So here, we actually didn't have to look at the results of the significant main effects, because this ANOVA, or these results, are saying that something more complicated is happening than a main effect. We can't explain the data only with these. We have to look at the full complexity of the data with the interaction. It's not appropriate to look at just 2 conditions, collapse, or 3 conditions. We have to look at the whole richness of the data in those 6 conditions. And we'll see how this applies to writing up in the manuscript a little bit later, but you'll see that in a manuscript, if I have a significant interaction, I'll say, yes, there's significant main effects, but then I won't even analyze them, because I'll say, they're overridden by the interaction, and then we need to analyze the interaction. So it's a little odd. This is where we get to our first kind of limitation of SPSS. That it's, remember with post hoc tests with a 1-way or main effect, got those 18 options. Here, you kind of have to convince it to run post hoc tests on interactions, which seems strange. So we have 2 options. One, we could run all full pairwise comparisons, compare every group to every other group. And the way you can do that is rerun the data as a 1-way ANOVA. So remember I gave that first example of, hey, if we just do a 1-way ANOVA with 6 conditions or levels, we could do that, and then SPSS would say, sure, I'll let you run those 18 post hoc tests. And we'll try doing that. The challenge with that is you're going to have a lot of pairwise comparisons. So you're going to have to make a correction for family-wise error rate, and your power is going to go down. And we probably have more comparisons than we really want or need. Usually you don't want to compare every group to every other group. So the second, more systematic approach, this is kind of like shotgun, let's try everything. Here, this is, hey, I have some specific questions about these data, and we can address those with simple main effects. Downside to these is SPSS doesn't let you click a button and say simple main effects. You have to edit the syntax or the code for the ANOVA. Fortunately, though, it's not too hard. So let's look at our first option. What we need to do to analyze these data as a 1-way ANOVA, we can't do that with having 2 grouping categories. We need 1 single one. So I've added a new column here for a 1-way ANOVA analysis where each condition gets its own unique number. So instead of 0 and 1 and then 0, 1, or 2, the groups are divided from 0, 1, 2, 3, 4, 5. And then we can just say, hey, let's run a one-way ANOVA. I call that column one-way group. We'll put that in as the factor, and it will run a one-way ANOVA. We don't really care about the F value. We're just doing this so that we can access the post hoc tests. And here I tried running 2P and RAGWQ. We don't want Bonferroni because we've got more than 3 conditions now. There are 6, so it likely have very low power. Here are the results. I'm just going with the table where we can compare these two to each other, see which one is more powerful. We look, 2P has put these two conditions together. RAGWQ has done the same thing. Here they have a p-value of 1.97. Here it's 0.069. This is a smaller p-value, so that means RAGWQ is a more powerful test on these data. And it really depends on your data. So we want to report the results of the RAGWQ because it's the more powerful test. And let's try to interpret them here. And what you'll see, when you make all the pairwise comparisons, it then gets complicated to explain what's happening. And this is often why I don't like to do this. It's complicated and there's a big hit to your power. So what does it say? It says, okay, well, unattractive 0.0 and unattractive 0.4 are comparable. So unattractive 0, unattractive 0.4. Okay, so although there's a visual difference here, statistically these two conditions are comparable. The next two power conditions are again 0.04, this condition again, and then attractive 0.07. So these two conditions are comparable. Okay. So this one's significantly different from this one, but this one is comparable to that one and to this one. And then our last group, we have this condition again. This one and this one and this one. So these ones are comparable, but significantly different from that one and that. Like, okay, that describes what's happening here, but interpreting that in terms of, well, what's the answer to our scientific question about the effects of what alcohol on attractive ratings is kind of a little confusing to pull out. So instead of going too far down that road, let's kind of go back to our second approach where we can do what are called simple main effects. There are 2 ways to run simple main effects for a 2-factor ANOVA or a 2-way interaction. If you had a 3-way interaction, there'd be 3 ways to run simple main effects. We'll look at both of those. There's 2 options here, and it is actually okay to run both if it's necessary, or if you have a very specific question, you might actually only run one because the other one may not be worthwhile to your research question. And both of these, even if you run both, there's going to be fewer comparisons than if we do full pairwise comparison. So the first thing we can do are simple main effects on phase type. So you can either do simple main effects on phase type or simple main effects on blood alcohol. So it's based on the factors you have. So if we run simple main effects on phase type, there's going to be 3 comparisons. So phase type, here we have unattractive and attractive. The first comparison is a t-test that says, are these 2 attractiveness ratings different? Out of blood alcohol of 0. Then out of blood alcohol of 4, we have a second comparison. This is another t-test. It says, are attractiveness ratings different here? And then we have a third t-test for on phase type for blood alcohol of 0.07. So instead of 15 full pairwise comparisons, if we do simple main effects on phase type, we just have 3 t-tests. And you might be thinking, oh, okay, we've got 3 t-tests, so maybe we need to use a Bonferroni correction, take 2.05 divided by 3. Well, part of the magic, or always a little bit like cheating, but that's how they work. So the way simple main effects works is they actually treat these different tests as kind of independent from each other. So this is, they say, okay, well, we're comparing 2 things. Do we need to control the Familywise area when we compare 2 things? No. So we use 0.05 here. Now we forget that we've done that in a way, and we come here and we say, okay, we're comparing two things. We don't care about that we might have done others. We're comparing two things. Do we need to adjust alpha? No. And then finally, forget that we've done those. We're comparing two things. Do we need to adjust alpha? No. So simple main effects, not only are they more powerful because we're not doing full pairwise comparisons, but how alpha is adjusted is a bit cheeky. And here we kind of get 3 t-tests for free, with no correction to the Familywise error rate. Now, what if we want to do simple main effects on alcohol? Well, then what we're going to do is we're going to look at unattractive bases, and we're going to look at, well, do those ratings change from an alcohol of 0.0, 0.4 to 0.7? That's, you can think of that like a one-way ANOVA. Now here, there are more than 2 possible groups or comparisons. We can compare those two, that's 1. Those two, that's 2. And these two, that's 3. And with simple main effects, they say, okay, now you've got 3 comparisons. So we are going to control the Familywise error rate now. So we now have 3 comparisons and not just 1. SPSS is quite limited. It will only allow you to pick LSD, which is no correction, Bonferroni, or CDAC. And we'll use Bonferroni, and thankfully, because there's just 3 conditions, Bonferroni is appropriate. But even if you had 10 conditions, it still only lets you pick between no correction and Bonferroni and CDAC. So a limitation to SPSS. So that's 1/2 of the simple main effects on alcohol. You can imagine the other half. We're now going to look at comparing blood alcohol concentration across attractive bases. And again, we have 3 comparisons here. There are those 2 conditions, those 2, and those 2. And we will control the Familywise error rate because we're making 3 comparisons there. But we don't have to control it as much as if we were making 15 comparisons. And it treats these comparisons and these comparisons independently. So we kind of get 3 comparisons per 3. So simple main effects are targeted, and they're typically applicable if you have a strong research question. If you're just going in and you're kind of like, oh, does anything happen to anything else? Well, then, you might need to do full pairwise comparisons, and you're going to have to control your Familywise error rate, and your power will decrease a bit. But you kind of think of these as either, horizontal comparisons or vertical comparisons. Okay. So I think for this experiment, because the question is really around how does attractiveness change based on blood alcohol, I think we can just do simple main effects on face time. Now what we can say is, if we think about the science behind this experiment, all right, so you haven't had any alcohol, we should likely see attractive faces are rated higher than unattractive faces. Now, keep consuming alcohol, a moderate amount, a high amount, and the hypothesis would be that here attractive faces are still attractive, but unattractive faces with the beer goggles effect have become attractive, and that's what this data shows. So I don't think we really need to do these comparisons to get at the answer to the answer to this meetup experiment. So how do we do that? Well, one thing that will help is if we pick another selection in SPSS. So we're going to go back to a univariate ANOVA. We probably still have a post hoc test like for alcohol. What we want to do though is go into EM means. And this isn't going to give us what the final output we need, but it's going to put a lot of the syntax in for us. So you can select all of these, move them over. We're not actually going to click off anything else, just say continue. And then we're going to paste this into the syntax editor here. And because we did that last step, these 3 lines are added. And what we want to do is just edit the interaction line. So if you hadn't have done that step, you wouldn't have any of this, and you would have to type all of that in. You actually don't need these 2. But by picking the EM means it kind of puts in half the syntax that we need. So what we're going to do here is we want to say compare, and then we want to select the type of simple main effect. So this, we wanted it on base type. And if you want to do simple main effects on alcohol, then you would put in alcohol instead. And then we're going to say, hey, let's do an adjustment for the Familywise error rate. And there's actually only 3 options: LSD, which is no correction; Bonferroni, that's the one we want; and then CDAC is also an option. But we'll go with Bonferroni. And let's say you happen to want to run both simple main effects. Well, you can actually just copy and paste this line. This properly, and you could say, hey, do this again, but do simple main effects on won't worry about that second one today. So we've got that now, and then the way to run your code is you highlight it and you click play. And this can be handy. So often when I'm working on studies, I'll typically just save my syntax so that later on I'm like, oh, exactly what did I run? Well, I haven't saved. I don't have to like write down, oh, I clicked this box and that box. This will save it for you. You could save your output as well. And let's see, when you run your output, it actually includes the code that you ran to get that above. Okay. So we can see a lot of the same things, and we'll skip down over here because we're starting to get a lot of output. But this is where the interaction is analyzed. And let's go back to SPSS and look at this. Sorry, not PowerPoint to programs. Go. So we get some descriptive statistics on top, and the main part that we care about is here. These are all the pairwise comparisons. And sorry that's a little hard to read. I mean, we should just focus on this part. But here it says, okay, at 0.00 blood alcohol, that's this here, it compares unattractive to attractive. So this is our first comparison. And here's our p-value. It says, yes, they are significantly different. This is a duplication of that test. It's just now it's attractive to unattractive, but it's the same thing in the opposite direction. So we don't need to worry about that one. It's also significant. So our first comparison, yes, there's a significant difference. Then our second comparison, we've got 0.04 blood alcohol. So now we're going to look at this vertical test. And is it significant? Yes, the p-value is 0.08. So we have a significant difference in attractiveness here. And then between attractive and unattractive bases. And then we've got one more comparison at 0.07. And we can see that the p-value is not significant now at 0.398. So if we think back to our question, we can look at the results here and say, okay, you haven't had any alcohol, and attractive bases are more attractive than unattractive bases. Makes sense. You've had a moderate amount of alcohol, and well, attractive bases are still more attractive or significantly more attractive than unattractive bases. It does seem like there's a trend for a change here, but to know that for sure, we have to analyze the simple main effects in the other direction. But we can see, once you're at a high level of alcohol consumption, that unattractive and unattractive bases become comparable. I think that just those 3 comparisons are really all we needed to answer the experimental question, which is much more powerful and a lot less confusing than looking at all 15 pairwise comparisons. These line charts like this, you can get, I think this is maybe from MATLAB, but you can get simple ones like these out of SPSS. The next slides show that, but I'll just go back to SPSS to show you. Oops. you will see that, the more kind of things you click off in SPSS, the longer that output becomes. So say univariate, it's going to have everything we have from before, except, it hasn't retained those simple main effects because that doesn't change anything here. It just changed our code. But if we want some plots, we can click on plots. And then you can say, hey, show me the main effect of face type. So we'll add that. Show me the main effect of alcohol. And then we really want to know about the interaction. Let's see, with our interaction, we had alcohol on the horizontal axis and face type were two different lines. So we'll add that. And here you can I don't think you can change them individually, but we can say, hey, let's make these all line charts. Hey, let's put on some error bars. We'll make those standard confidence intervals, not the best, but we don't have the option for difference adjusted ones here. Although we could pick standard error and then find out what the t-value multiplied by the square root of 2 is, and that would give us difference adjusted confidence intervals. Continue and run this, and the plots will be at the very end. They're not the quality you want to put in your manuscript, but we're just kind of looking at the data, understanding the significant effects there. It can be very helpful. There we go. Okay. So there's our main effect of face type, which was significant. Our main effect of alcohol, where we saw a significant difference between the lowest and highest conditions. And then here's our interaction, where we saw these are significantly different, these are significantly different, and then these are not significantly different. So any questions on analyzing the interaction? You can also ask for bar graphs, which are more appropriate here. Typically, line graphs are used when there's a time series to your data. So if this was like pre-test, post-test 1, post-test 2, that would make sense. But because there isn't an inherent time between these, you shouldn't use a line graph. You can ask SPSS for bar graphs, but with interactions, we kind of like to look at the lines, as we'll see more later. So often I just like the line graphs in SPSS, and then the manuscript I would use a bar graph if there's no time series to your data. So effect size. When I reported the ANOVAs earlier, we had an F value, a P value. We didn't have an effect size, and with one-way ANOVA, we could report eta squared. For a factorial ANOVA, I think it's better to report partial eta squared. And what this will do is this will give you the size of the effect. It's going to give you a score between 0 and 1, 0 meaning 0%, 1 is 100%. And that's the how much variability does a factor explain out of the total variability. And you can see here, if you had a partial eta squared of 1, all the variability is accounted for by that factor or interaction, that would be surprising. So the standard effect sizes are actually quite lower. 0.14 is actually you're explaining 14% of variability in the data. That's actually a large effect size. So we can calculate these by hand. So if we want to know what is partial eta squared for face type, we have to take the sum of squared of face type. So we come over here to this column, don't use your mean squares. That's not going to work out for you. So it's 21.333. And it's divided by the sum of squared face types, that same value, plus sum of squared of the error. And the error term is the same for the main effects and the interaction. And that gives us a value, once we round to 2 decimal places, drop the leading 0 because it ranges from 0 to 1 of 0.27. We can do this for the other main effect, and we can also do it for the interaction. So each one will range between 0 and 1. But the nice thing is SPSS, we can ask for it to calculate these for us. So if you go into options, you can click, I often like to add descriptive statistics that will give you, your mean, your standard error, your confidence intervals for your 6 conditions. And I can say, okay, please also give us estimates of effect size, and SPSS uses partial at a square. Another reason I love to use. So there's our, descriptive statistics. That is another box that would add to the output, which is, getting a bit long now. And then here, when we look at our ANOVA table, so we saw our F values, our P values, and we've added another column. We now have partial N squared. And these are the same values that we get if we do it by hand. Let me show you that again. So the way you would report that is you would just add partial N squared to the end of your statistics. Let's just do one because I forgot to add them here. We'll see them later in the main script. Let's see. Let's maybe do the interaction. So it's F2 42, 242. Our F value 8.51. Tell me if I'm doing anything wrong here. P value was very little, so we'll say less than 0.01. And now partial squared. With the value range in 0 and 1, so like the P value, we drop to 0 and 0.29. Nothing too crazy, just add it on to the end. Now, the shortest section for this talk is the section on assumptions. Remember I said that the more complicated the statistical analysis gets, the more we're like, I'm sure it meets the assumptions. And we see that here. So, the data should be continuous. You definitely don't want to violate that. We could look for outliers. We could look at normality. The data should be independent. That's kind of another given, just like it should be continuous. Equal variance. Remember before we had, Levine's test? Well, SPSS won't do that for us anymore. There's a great quote from the textbook. So before, with a one-way ANOVA, we could do the Brown, Forsyth, or the Welch corrections. Now SPSS will not, because it's basically too complicated. There's too much statistical argument in current literature on how to make a correction for unequal variance. And the textbook, I love this quote, it says, it would be less painful to cover your body in paper cuts and then bathe in chili sauce. So we don't even check for equal variance because it basically, can't fix it. All right.
You're gonna have to do that on the assignment.
Bathe in chili sauce?
Yeah.
Oh. Maybe in the advance. Almost done. So let's look at the method section and the results section. Method is still pretty short. Results is going to be a bit longer because we need to explain that interaction, and that takes a bit of work. So I say at 2 face type, and then I give the levels. By 3 blood alcohol, ANOVA was used to compare attractiveness ratings. Effect size was reported using partial N squared. The significant interaction was analyzed with simple main effects on face type. And because that was 3 t-tests, we actually didn't have to do any family-wise error correction. So I didn't say anything about that. If we had done simple main effects on blood alcohol, then it would have been 3 pairwise comparisons, 3 pairwise comparisons. We would have needed to do a correction for the family-wise error rate, and I would have added in a sentence about that. I also didn't say anything about confidence intervals because we're getting so many conditions now that listing all that data would be a bit messy, and it's easier now to do a table or a figure, and I've chosen to do a figure. And then typically the figure caption would say exactly what the confidence intervals are. So there's my figure. And I've even tried to illustrate the significant differences, so we compared the blue bars, they're significantly different. The orange bars, significantly different. Orange or, yeah, how would I refer to these two colors? Dark orange, light orange, is this orange, is that not orange? Yellowish, is that more yellow? I'm bad at color names. We'll call this blue, orange, and yellow.
Yeah, it looks yellow.
Okay. I remember, I think the first time I realized I wasn't very good at knowing the names of colors. So I was playing StarCraft, and I was playing with a friend. He's like, "Oh, which color are you?" Because each army, the color would be different. I'm trying to remember. I think I said I'm dark yellow. And he's like, once he found me, he's like, "That's orange." It's dark yellow. So restating the ANOVA that you're using, that's optional. Kind of depends. If you like reiterating things, and here, we just read the method section, so this is immediately thereafter. You probably don't have to repeat yourself. But if you got a long method section, and then it's like pages into the results before you come back to this, you could remind a reviewer of what you're running. So there were significant main effects of base type and alcohol, and then comma, I give the F values for that. Some people might splice in significant main effects of base type, statistical results, alcohol statistical results. That's okay. I don't like to do that because mixing the numbers and letters, it's harder to read. So I like to group, words together, numbers together after. But down here you'll notice, this would be the results for base type. Base type, and then that would be from there would be the main effect of alcohol. Now I'm not going to analyze those because they're overridden by the interaction. And I say these were, however, overridden by significant base type by alcohol interaction, and then I give the statistical support for that. So now, we don't need to worry about what's going on with the main effects because more importantly, there's an interaction, and we're going to analyze it. And I guess this is a bit of a repetition from the method section, so optional. Well, I guess it's not too much. We're just saying, hey, simple main effects. Simple main effects on face type suggested that unattractive faces had lower ratings than attractive faces at 0.001 alcohol concentration. I give my p-value to support. That is our first comparison. And I say unattractive faces still had lower ratings compared to attractive faces at 0.04. Probably it's a blood alcohol after that. Gave my p-value there, so that's this comparison. However, at 0.07, however, ratings for attractive and unattractive faces were comparable. That this third comparison is not significantly different. That's its p-value. And that may be as far as you go in the results section, and then in the discussion there'd be more interpretation of what this means, addressing your experimental question. All right with those results? So it's getting longer, but not too crazy. We're going to talk a little more about interactions and come back to the idea of family-wise error rate. Let's just look at interactions first. So here, I'm going back to look at the simplest possible interaction, and that would be a 2x2 interaction. So you've got two factors, each with two levels. The beer goggles experiment, it's slightly more complicated. It's a 2x3. So just 3 instead of 2. But let's just think about a 2x2. So it's the simplest possible data set. And I don't know if the context matters too much, but here I've kind of made up that there's an experiment where you're doing movements either without vision or with vision. And then some participants either move to a short distance target or a long distance target. So we have a group of participants that do this, another group that does this, and another group, and another group. Each participant participates in only one of these conditions. So it's a 2x2 ANOVA. So let's say the results look like this. I'm trying to show the exact same value in every single condition. I separated the lines a little just so we can see that there's two lines here. So what we would see here is that there should be no main effects or interactions. I'm saying, well, it doesn't matter if it's it's vision, no vision, short or long, it's people's reaction time is always the same. And the way you would report this is, well, you would say, there are no significant main effects or interactions given statistical support. And then all you need to describe these data is just with the grand mean. Say, well, reaction time was 250, if you have any sort of confidence interval around that. But this would be the simplest case where you do a factorial ANOVA, and there's no main effects or interactions. Basically, all data points are comparable or identical. I mean, one might be a little higher than another, but statistically, everything is comparable. What if we had a main effect of vision, but no main effect of distance and no interaction? Well, it would look something like this. It could be this way, it could be that way. But basically, what we would have is a difference between vision and no vision. So, kind of like a t-test, right? But if we compare short and long, well, they're the same here, and they're the same here. So it doesn't actually matter whether it's the short or long distance target. So these data, we would see a significant main effect of vision and nothing else. What about a significant main effect of target distance? That could look like this. It could be this, it could be this. It could be a little difference, could be a big difference. But here we could potentially see a main effect of target distance. So now it makes a difference whether the target distance is short or long. Does it matter whether it's vision or no vision? Nope. Comparable. Comparable. The only difference is in target distance. So we have a main effect of target distance. Now, what about if we have two main effects? So a main effect of vision, target distance, but no interaction. That's another possibility. Then your data should look like two parallel lines. And they also shouldn't be horizontal because that would just be one main effect. So two parallel lines, so it could be like this, steeper. It could be the other way. But you should have two parallel lines that are not horizontal. So, but these data can be explained by two main effects. There's no interaction going on here. Now, what about an interaction? And with these interactions, you may or may not have main effects, but in some ways it doesn't matter because the interaction would overrule that. Now, a classic interaction for a 2x2 ANOVA is X, and that's why I used the treasure map on the first line. X marks the spot, and X. That's that you probably going to have an interaction. And here, you can't just talk about vision or target distance. You have to talk about those combined. Because it makes a critical difference. Let's say, so if it's a short target, with vision you're fast, with no vision you're slow. But if it's a long target, the exact opposite happens. So you have to talk about the combination or the interaction between those factors. So an X is a classic interaction. You might see this in SPSS. It might not be significant because SPSS, those graphs will zoom in on your data. So if you zoom out, it might be a tiny, tiny X. So you still need to test. You can't just see an X, you have to see it a significant X, if you will. Interactions can also occur when the lines are significantly not parallel. It doesn't have to be an X. It could be something like this. As long as there are significant differences there, those lines are not parallel. It could be like this. Any other examples? I guess those are three. So basically, non-parallel lines, that's when you're potentially going to see an interaction, depending on whether it's SPSS deems it to be significant. Any questions on interactions? Last thing, I just wanted to touch on the family-wise error rate. So remember, t-test, family-wise error rate 0.05. One-way ANOVA, at least for the omnibus test, family-wise error rate is 0.05. You might then think that with a factorial ANOVA, the family-wise error rate is 0.05, until we get to the post-hoc test, but it's actually not. And the way it works with ANOVAs is that the family-wise error rate is 0.05 for each main effect and interaction. And we'll look at examples of 2, 3, and 4-way ANOVAs, and this, of course, could be extrapolated higher. Although I can't say I've seen a 5-way ANOVA very recently in research I've read. I mean, you can think about how hard it was for us to analyze the interactions. It wasn't that hard, but we had to kind of go to some depth. Now imagine that getting exponentially harder every factor we add, and that's a good reason not to run a 5-way ANOVA. So with a 2-way ANOVA, so we can think about the one we just ran. We don't care how many levels there are, but for the mean effective phase type, there is a Familywise error rate of 0.05. For blood alcohol, also another 0.05. I guess I should say the Familywise error rate alpha is 0.05 here, 0.05 here. For the interaction, it's also 0.05. So we have 3 comparisons, if you will. We can go back to our good formula for Familywise error rate, put the number of comparisons to 3, set our alpha to 0.05, which is typical. And we're going to see that the Familywise error rate for a 2-way ANOVA is actually 0.14 or 14%. So the Familywise error rate is maybe not what you think at first glance with a Factorial ANOVA. And that's maybe another reason not to run a 5-way ANOVA, is because the Familywise error rate is going to be rather large. It's no longer 0.05. Although this does seem to be something that's kind of fairly accepted, that's kind of just how it works. Here's a 3-way ANOVA. So again, it doesn't matter how many levels there are until we get to post hoc tests, which we're not going to worry about. That gets pretty complicated. Does anyone remember this SNL skit? Yeah, it's still out there in the internet. That's good. Wasn't sure. I was like, will anyone know this? If you don't know, you can look that up. So with the 3-way ANOVA, there's going to be 3 main effects. So factor 1, factor 2, factor 3. There's going to be 3 2-way interactions, and there's going to be 1 3-way interaction. So you can see, yeah, if these, some might be significant, some might not be significant. That's a lot of data to analyze. But each one of these has an alpha of 0.05. So we've got 7 comparisons. We'll plug that into our favorite formula here, and we get a family error rate of about 30%. What about a 4-way ANOVA? Oh, here, we got to move this so you can read that. I found this driving website. I almost feel like I should have leaflets for this and hand them out to.
It's very applicable.
Yeah, I've heard Texas in
But
general.
they err on the side of letting you go when they don't have to hear it.
Sometimes that frustrates me too.
Yeah, like slows everything down.
I've learned if you know you were there first, go.
Go, yeah.
Or else you're both going to be there like, no.
So 4-way ANOVA, we've got 4 factors. Let's see, how many 2-way interactions? I think that's 6 2-way interactions. So this is getting crazy, right? 3-way interactions, well, there's only 4. And then we're going to have 1 4-way interaction. So I've lost count, but that gives us a total of 15 pairwise comparisons. Yeah, I guess we've seen that before. So the Familywise error rate for a 4-way ANOVA, even before going into the post hoc test, is about 50%. So there's a 50% chance you made at least 1 false positive.